We're looking at the equilibrium behavior of the current in a circuit with inductance L and resistance R. And in this case, we are assuming that the energy put in, or for that matter taken out of the system, is constant E. So we have that the derivative of the current over time is E over L minus R over L times the current. It's fairly easy to check that the only equilibrium point is E over R for the current. And so here's the equilibrium point on the line for the current. And if the current is above this equilibrium point, regardless of whether E is positive or negative, I prime is negative. And if we're standing at a level of current below E over R, then I prime is positive. And so this is a sink, and that's where the system winds up qualitatively. You can actually think of an analogy with a spring, assuming that the energy is positive, so that there's a net force in the direction of increasing the length of the spring away from equilibrium. You can imagine a pulley here with a weight that keeps a constant force in this direction, and then we have the spring constant. So the R over L is the analog of the spring constant, and E over L is the analog of the force here. And it's pretty obvious that the spring might oscillate, but it'll eventually settle at a place where there's a balance between this force and the force of the spring.